Hi everyone, welcome back to our video series on utility theory and health technology assessment. In this video, we're going to be talking about index conversion to the 0-1 interval. Let's go. So in our previous video, we've discussed several ways of measuring health utilities and having said without proof that standard gamble is the most theoretically sound way of measuring these utilities. This is because unlike time trade-off and the visual analog scale, there was no strict reason to keep utilities on a 0-1 interval other than as a normalization. In this video, we'll show that defining health states on the 0-1 interval, aside from being convenient, is a theoretically sound way of ranking and quantifying differences between health states. We'll be drawing heavily upon the results from the expected utility representation theorem. We won't prove this result in its entirety, but we'll rather utilize several intermediate lemmas for demonstration of a utility function which represents preferences over health states that we desire. Before we do this, though, we need some basic language regarding preferences over lotteries. So, as our preliminaries, we need to note that traditionally, the way we think about choices over health technologies is as choices over lotteries. This is because every treatment plan, and even a choice to not engage in a treatment altogether, has with it some degree of uncertainty. We define a lottery as a list, right? P1 to Pn, which each Pi being greater than or equal to 0 for all outcomes I, and that the sum of each of these Pi terms are equal to 1, where Pi is the probability of outcome I occurring. In a case where there's a lottery that has a certain outcome with it, let's call this Li, right, which goes from 1 to n, where Pi is equal to 1 and everything else is equal to 0, we call this a degenerate lottery, with outcome I occurring with certainty. We imagine that there is a way to go and rank these lotteries from most preferred to least preferred on this finite list of lotteries, script L. We note that there is a most preferred lottery, L bar, and least preferred lottery, lower L bar, in this finite list of lotteries. This is all we have to know for right now. So now defining a utility function with a 0-1 interval that goes and represents our preferences over lotteries, we need really three lemmas, and these come directly out of our expected utility representation theorem. In our context, I'm just going to call this lemma 1 and lemma 2, and this theorem, which is going to be our primary result. The first lemma that we're looking at is that we're going to say we have two scalars, alpha and beta, on this closed interval of 0 and 1. Then we'll say that this convex combination between the best preferred and least preferred lotteries under beta is going to be strictly preferred to that convex combination under alpha. And that's only true if and only if beta is greater than alpha. There's a proof for this, but so far, so good. Lemma number 2 is that if we have for any L in our finite space of lotteries, there is going to go and be a unique alpha L on this closed interval such that there we can go and use this convex combination between this least preferred and most preferred lottery to be indifferent to that L, right? So for any L in this value, and this is pretty powerful because we can go and bring in all other lotteries in our lottery space as defined by our most preferred and least preferred lottery, right? And that's seen, primarily in the context where we're looking at, degenerate lotteries, right? Outcomes with certainty that we go and we have there, the best outcome with certainty, like that's probably the best lottery that you're going and you're looking at, and the worst outcome with certainty, right? You could go and span that whole space there, but even if you have a little bit of uncertainty in there, you could go and pull this through. This theorem that we're going to go and have together with these two lemmas, we're going to go and state that there is a function u, right, that assigns each alpha L for all lotteries in our lottery space. That's going to go and represent our preferences over lotteries. And the way we go and we prove this is that we're going to observe that for any two lotteries, we have a case where we have L being at least preferred to L prime if and only if this convex combination under alpha L is going to be at least as good as the convex combination under alpha L prime. Appealing to lemma 1, right, where we go and we have this here, this is only true if and only if alpha L is going to be greater than or equal to alpha L prime. Thus, the function u represents preferences over lotteries. So this utility function here could go and represent all our preferences over these lotteries here. So what does this theorem do for us? So this theorem allows us to transform one index into another with ease and generate a utility function u on the part of our quality calculation with ease. Perhaps this is going to be a quality which does not make our clinicians very happy, because we could go and use an index which does not embody all aspects of the quality of life that we're looking at. But it's something that satisfies the interval property and being preserved on a 0-1 interval. It's a theorem which allows for more medically focused scoring tools to be employed in the context of economic evaluation. So you can go and take whatever measurement tools that clinicians are going and using and apply them directly to your economic evaluation. So let's talk about converting index numbers on the 0-1 interval using standard gamble. So recall, what we seek to do in the context of standard gamble is that we want to go and identify the utility associated with a particular health state. And what we essentially go and ask is, what would go and place a individual indifferent between a gamble between perfect health and some worst imaginable health state, and taking on that health state I, which is unvalued. But if we go and we have already pre-existing index that we go and we have here, our work is pretty much done. It's just a matter of algebra. We're going to suppose that we don't have a clean index here, right? We're going to be thinking about something like the Princeton U-Matter Wellness Self-Assessment, which is on index from 7 to 28 for individual categories and 49 to 197 for summed values. So this is something that is clearly a mess. How do we go and deal with this here? So we're going to go and focus on these values, p and 1 minus p, and we're going to go and ask the question, for what value p does the quality hold, right? That this gamble between this utility in the highest health state, right, which would be 197, and the lowest health state, which would be 49, that would go and generate this known value hi here. So that's how you would go and address this. So that's all in this video. Want to go and make it to really go and express that standard gamble is the most theoretically sound way for going and getting these utilities, and it's also really good for going and converting one index to another index. So I hope this video helped, and I hope it was useful. Take care.